From the soaring grace of eagles to the delicate flutter of butterflies, nature has always held the secrets to flight. Observe closely, and you'll notice a recurring theme: symmetry. This symmetry is not just a visual delight but a crucial element in the mechanics of flight. Birds, insects, and even seeds borne by the wind all exhibit a balance in their physical structure. This balance allows them to harness the air currents and navigate with precision. This symmetry is not merely aesthetic, it is fundamental to their ability to navigate the air. The even distribution of weight and the mirrored design of wings and other appendages ensure stability and control. Early attempts at human flight, like Leonardo da Vinci's flying machines, mirrored nature's blueprint. Da Vinci meticulously studied birds and their flight patterns, translating these observations into his designs. These designs, often featuring flapping wings, sought to replicate the symmetrical elegance of birds. The idea was to mimic the natural world as closely as possible, believing that nature's designs held the key to human flight. While these endeavors ultimately fell short, they laid the groundwork for our understanding of the fundamental principles of flight. Each failure was a step closer to success, providing invaluable lessons for future inventors. The Wright brothers, pioneers of powered flight, also embraced symmetry in their iconic Wright Flyer. Their meticulous attention to balance and proportion was key to their groundbreaking achievement. Their aircraft's wings, control surfaces, and even its twin propellers all reflected a balanced design. This symmetry was not just for show, it was essential for the aircraft's stability and control. This symmetry was crucial to achieving stable and controlled flight, marking a pivotal moment in aviation history. The Wright brothers' success demonstrated the importance of balance and symmetry in aircraft design. However, as our understanding of aerodynamics deepened and our ambitions soared higher, it became evident that nature's blueprint, while elegant, had its limitations. Engineers began to explore new designs that pushed the boundaries of traditional symmetry. The pursuit of faster speeds and greater efficiency led engineers to question the constraints of symmetry and explore radical new concepts in aircraft design. These innovations have paved the way for the advanced, high-performance aircraft we see today, proving that while symmetry is beautiful, breaking the mold can lead to extraordinary advancements. The pursuit of progress often necessitates a departure from convention. In the world of aviation, this departure has led to some of the most groundbreaking advancements in technology and design. The skies have always been a realm of innovation, where engineers and scientists push the boundaries of what is possible. In the realm of aviation, this meant challenging the long-held principle of symmetry. For decades, symmetrical designs were the gold standard, providing stability and predictability. However, as aircraft began to fly faster and higher, these designs started to show their limitations. As aircraft ventured beyond the familiar realm of low-speed flight, new aerodynamic challenges emerged, demanding innovative solutions. High-speed flight introduced a host of new variables, from increased drag to unpredictable turbulence, that symmetrical designs struggled to manage. One such challenge was the phenomenon of transonic flight, the treacherous zone where an aircraft's speed approaches the speed of sound. In this zone, the behavior of air around the aircraft changes dramatically, leading to the formation of shock waves. At these speeds, shock waves form, creating tremendous drag and instability. This not only affects the aircraft's performance but also poses significant risks to safety. Engineers had to find ways to mitigate these effects to ensure smoother and safer flights. Symmetrical wing designs, well suited for subsonic flight, struggled to cope with these aerodynamic hurdles. The need for a new approach became evident as traditional designs failed to deliver the required performance at higher speeds. Enter the concept of asymmetry. This radical idea proposed that by deliberately introducing asymmetry into aircraft designs, engineers could better manage the complex aerodynamic forces at play. Engineers began to explore unconventional aircraft configurations, deliberately introducing asymmetry to improve performance. This involved extensive testing and experimentation, often in wind tunnels and through computer simulations, to understand the benefits and trade-offs of such designs. This marked a radical departure from traditional design principles, pushing the boundaries of aeronautical engineering. The journey was fraught with challenges, but the potential rewards were too significant to ignore. Asymmetrical designs offered the potential for improved lift-to-drag ratios, enhanced maneuverability, and reduced drag at transonic speeds. These benefits could lead to more efficient and capable aircraft, opening up new possibilities for both military and civilian aviation. The quest for asymmetry led to the exploration of various unconventional configurations, paving the way for revolutionary designs like the oblique wing. These innovations continue to inspire the next generation of aircraft, proving that sometimes breaking the rules is the key to unlocking new frontiers. The sound barrier, once an insurmountable obstacle, represented a defining challenge in the pursuit of high-speed flight. For decades, engineers and pilots alike were fascinated by the idea of breaking through this invisible wall in the sky. As aircraft approached the speed of sound, approximately 767 miles per hour at sea level, the air around them behaved unpredictably. Pilots would experience a sudden increase in drag, and a phenomenon known as buffeting, where the aircraft would shake violently. This unpredictable behavior stemmed from shock waves, abrupt changes in air pressure that formed as an aircraft neared Mach 1, the speed of sound. These shock waves were not just a minor inconvenience, they posed a significant risk to both the aircraft and its pilot. These shock waves created immense drag, causing buffeting and instability, making it extremely difficult to control the aircraft. The increased drag would often lead to a loss of speed, making it seem almost impossible to push through the barrier. Breaking the sound barrier required not only powerful engines but also a fundamental shift in aircraft design. Engineers had to rethink the very shape and structure of aircraft to make them capable of withstanding the intense forces encountered at such high speeds. Early attempts to breach this barrier often ended in disaster, highlighting the limitations of traditional aerodynamic principles. Many brave pilots lost their lives in these early experiments, underscoring the perilous nature of this quest. The quest to conquer the sound barrier spurred a revolution in aviation, leading to the development of swept wings, supersonic airfoils, and other innovations that transformed aircraft design. These advancements not only made supersonic flight possible, but also paved the way for future innovations in aerospace technology. The innovations that emerged from this era were not limited to just breaking the sound barrier. They also included advancements in materials, propulsion systems, and flight control technologies. These breakthroughs had far-reaching implications, influencing both military and civilian aviation. It was amidst this era of supersonic ambition that the concept of the oblique wing emerged as a radical and promising solution. This innovative design aimed to reduce drag and improve efficiency at high speeds, representing yet another leap forward in the relentless pursuit of faster and more efficient flight.